Welcome to this problem walkthrough. Today, we'll be diving into problem number 128, longest consecutive sequence. This problem is a classic in coding interviews, testing your ability to work with arrays and optimize for time and space efficiency. Let's take a closer look at the problem and explore strategies to solve it. In this problem, you're tasked with finding the length of the longest sequence of consecutive integers in an unsorted array. For example, given an array like nums equals 100, 4, 200, 1, 3, 2, you would need to identify the sequence 1, 2, 3, 4 and return its length, which is 4. However, the key challenge here is to design an efficient algorithm that runs in O(n) time, meaning you can't afford to use brute force approaches that would involve sorting or nested loops. The input array, nums, can have up to 100,000 elements, and each number can range between -1 billion and +1 billion. Your output should simply be the length of the longest consecutive sequence, as an integer. For instance, if we take the input nums equals 100, 4, 200, 1, 3, 2, the output would be 4. This is because the longest consecutive sequence in this array is 1, 2, 3, 4. Notice that these numbers may not appear consecutively in the original array, but they form a sequence when considered together. Another example is for the input nums equals 0, 3, 7, 2, 5, 8, 4, 6, 0, 1. Here, the longest consecutive sequence is 0, 1, 2, 3, 4, 5, 6, 7, 8, and its length is 9. In the second example, the sequence 0, 1, 2, 3, 4, 5, 6, 7, 8 spans across numbers that are not necessarily adjacent in the array, but together they form the longest consecutive progression. The output is therefore 9. For a third example, if the input array is empty, such as nums equals, there are no numbers to form any sequence. As a result, the output is 0. This demonstrates how the algorithm should handle edge cases like an empty array gracefully. Now, consider an example where the input array has only one element, such as nums equals 10. In this case, the single number itself forms the longest consecutive sequence. So, the output is 1. The algorithm must also account for constraints like the size of the array, which can range from 0 to 100,000 elements, and the value of each number, which can be as large as 1 billion in magnitude. The efficiency requirement of O(n) time complexity ensures that the solution will scale well for large arrays. Finally, let's discuss some important edge cases. If the input array is empty, the output should be 0, as there are no numbers to form a sequence. For a single element array, the result should always be 1, because the single number forms the longest sequence. Arrays with duplicate values, such as nums equals 1, 2, 2, 3, should still produce the correct result by ignoring duplicates. For example, this input yields a sequence of length 3, which is 1, 2, 3. Lastly, if the array contains no consecutive numbers, like nums equals 10, 20, 30, the result would simply be 1, as each number individually forms its own sequence. These edge cases highlight the robustness required in your implementation. To tackle the problem of finding the longest consecutive sequence, the first approach we could consider is the brute force method. Here, the intuition is straightforward. For each number in the array, identify if it is the start of a sequence. A number is considered the start if there is no smaller number in the array that precedes it, meaning that number 1 is not present. Once we identify a starting number, we incrementally count consecutive numbers to determine the length of the sequence. While this approach is simple and easy to understand, the downside is its inefficiency. For each number, we repeatedly check the presence of other numbers in the array, leading to a time complexity of O(n) squared. The space complexity, however, is O(1), since no additional data structures are used. While conceptually clear, this method struggles with large arrays due to the nested iterations, making it impractical for real-world scenarios where efficiency is critical. A more efficient solution uses a hash set to leverage constant time lookups. The key insight here is that a number can only be the start of a sequence if it has no predecessor, meaning number 1 is not present in the set. To implement this, we first add all the numbers in the array to a hash set, which allows for quick lookups. Then, as we iterate through the array, we check each number to see if it qualifies as the start of a sequence. If it does, we count the consecutive numbers by incrementing from that number and checking the set for the next values in the sequence. During this process, we keep track of the maximum sequence length. This approach is highly efficient, with a time complexity of O(n), since each number is processed at most twice. However, it does require additional space for the hash set, resulting in an O(n) space complexity. Despite this trade-off, it is far more practical than the brute force method for large datasets. Another strategy to solve this problem involves sorting the array. Once the array is sorted, consecutive sequences become adjacent, making it easier to identify and count them. To implement this, we first sort the array, which takes O(n) log n time. Then, we iterate through the sorted array and compare each element with the previous one to determine if it continues a sequence. If it does, we increment the current sequence length. If it doesn't, we reset the count and update the maximum sequence length if the current one is longer. While this approach is conceptually simpler than the hash set method, it does not meet the O(n) requirement due to the sorting step. The space complexity is O(n) if sorting requires additional space, or O(1) if sorting is done in place. Although effective for some scenarios, this method falls short in terms of efficiency when compared to the optimized hash set solution. The most efficient and practical strategy for this problem is the optimized hash set approach. The key observations here are that a number can only be the start of a sequence if its predecessor, number 1, is not present, and that a hash set allows us to efficiently check for sequence starts and count consecutive numbers. What makes this approach particularly powerful is how it avoids redundant sequence checks. By focusing only on numbers that qualify as sequence starts, we eliminate unnecessary processing of elements that are part of ongoing sequences. This ensures an O(n) time complexity, which is optimal for this problem. While the use of a hash set requires additional space, this trade-off is reasonable given the efficiency gains. Compared to both the brute force and sorting methods, the hash set approach is superior in both time complexity and scalability. Ultimately, it is the best choice for solving this problem, especially when dealing with large datasets, as it directly satisfies the problem's constraints and offers a robust and elegant solution. To solve the problem of finding the length of the longest consecutive sequence in an unsorted array, we aim for an efficient approach rather than brute force. Imagine an input array like 100, 4, 200, 1, 3, 2. The longest consecutive sequence here is 1, 2, 3, 4, with a length of 4. To achieve this efficiently, we use a hash set-based solution. First, we convert the input array into a hash set. This allows us to perform lookups in O(1) time on average. For instance, converting the array 100, 4, 200, 1, 3, 2 into a hash set results in 100, 4, 200, 1, 3, 2. This structure is key to quickly finding and managing consecutive elements in the array. Once the hash set is created, we iterate through each number in it. For each number, we determine if it is the start of a sequence. A number qualifies as the start if the number just before it, number 1, is not present in the hash set. This ensures we only start counting sequences from their smallest element. For example, in the hash set 100, 4, 200, 1, 3, 2, the number 1 is the start of a sequence because 0 is not in the hash set. However, 4 is not the start of a sequence because 3 is present. If a number is identified as the start of a sequence, we then count the length of that sequence by checking for the presence of consecutive numbers, such as number plus 1, number plus 2, and so on. For instance, starting from 1, we find 2, 3, and 4, forming the sequence 1, 2, 3, 4, which has a length of 4. A variable is used to track the maximum sequence length, updating whenever a longer sequence is found. For example, after processing 1, 2, 3, 4, the maximum length would be 4, and sequences like 100 or 200 would not change this value. After iterating through the hash set and identifying all sequences, we return the value of the max_length variable, which holds the length of the longest consecutive sequence. This approach avoids redundant work by only starting sequences from their smallest number, skipping over numbers that are already part of a previously processed sequence. The use of a hash set ensures efficient lookups, making this algorithm far more optimal than a brute force approach. While the hash set requires additional space, the significant reduction in time complexity to O(n) justifies this trade-off. Thus, this method balances space and time efficiency effectively. Analyzing the complexity, the time complexity is O(n). This includes O(n) to populate the hash set and another O(n) to iterate through the hash set and process the sequences. The space complexity is also O(n) due to the storage requirements of the hash set. Considering edge cases, for an empty array, the output is 0 since no sequence exists. For an array with a single element, such as 10, the output is 1 since the sequence length is 1. If all elements in the array are duplicates, like 2, 2, 2, the output is still 1 as there is only one unique number. For disjoint numbers, such as 10, 100, 1000, the output is also 1 as no consecutive sequence exists. For an already sorted array, such as 1, 2, 3, 4, 5, the entire array forms a single consecutive sequence, so the output is its length, which is 5. This demonstrates the algorithm's ability to handle various input scenarios effectively, ensuring accurate results for both typical cases and edge cases. With its O(n) time complexity and robust handling of edge cases, this method is a highly efficient solution to the problem of finding the longest consecutive sequence in an unsorted array. This solution uses a hash set to efficiently determine the length of the longest consecutive sequence in an array. The code begins by converting the input array nums into a set called number_set. This conversion ensures O(1) lookups for each element, which is critical for optimizing the solution. Next, we initialize a variable longest_streak to keep track of the maximum sequence length found so far. The algorithm iterates through each number in the set. For each number, it checks if it is the start of a sequence by verifying that its predecessor, number 1, is not in the set. If this condition is true, it means the current number is the smallest element in a potential consecutive sequence. We then initialize current_number to the current number and current_streak to 1, as this number itself constitutes a sequence of length 1. Next, the code enters a while loop to expand the sequence by checking if the next consecutive number, current_number plus 1, exists in the set. If it does, the algorithm increments both current_number and current_streak, effectively extending the sequence. Once the sequence can no longer be extended, the maximum streak, longest_streak, is updated if the current streak is longer than the previously recorded maximum. This process continues for all numbers in the set. By ensuring that each sequence is only processed once starting from its smallest number, the algorithm achieves a time complexity of O(n), where n is the size of the input array. This efficiency makes it suitable for large datasets. The function finally returns the value of longest_streak, which represents the length of the longest consecutive sequence found in the array. In this implementation, we start by importing the necessary libraries and defining our solution class. The method longestConsecutive takes an array of integers, nums, as input. The first step is to use a hash set to store all the elements from the array. This allows for O(1) lookups, which is critical for ensuring the algorithm runs efficiently. Next, we initialize a variable longestStreak to track the length of the longest consecutive sequence. Then, we iterate through each number in the hash set. For each number, we check if it is the start of a potential sequence by confirming that the number immediately before it, number 1, is not present in the set. If this condition is true, it means we can start building a sequence from this number. We initialize two variables, current number to track the current number in the sequence and current streak to count the length of this sequence. Now, within a while loop, we continue expanding the sequence by incrementing current number as long as the next number, current number plus 1, exists in the set. Each time we find a consecutive number, we also increment current streak. Once the while loop ends, meaning there are no more consecutive numbers to expand the sequence, we compare the current streak with longest streak and update longest streak if the current sequence is longer. After completing the iteration through all numbers in the hash set, the method concludes by returning longest streak, which holds the length of the longest consecutive sequence in the input array. This approach ensures an optimal time complexity of O(n), as we only iterate through the numbers and perform constant time operations for each. The use of a hash set allows us to efficiently handle lookups and ensures the algorithm remains scalable even for larger input sizes. To solve this problem efficiently, we start by converting the input array nums into a set called number_set. This allows us to perform lookups in constant time, which is critical for our approach. We also initialize a variable longest_streak to 0, which will keep track of the longest consecutive sequence found so far. Now, as we iterate through each number in number_set, the first number we encounter is 1. Since 0 is not in number_set, we know that 1 is the start of a new sequence. We initialize current_number to 1 and current_street to 1. We then check if 2 exists in the set, which it does, so we increment current_number to 2 and current_street to 2. Similarly, we find 3 and 4 in the set, incrementing both variables accordingly. However, when we look for 5, it's not in the set, so we stop the sequence and update longest_streak to the maximum of its current value in current_streak, which is 4. For the next number, 2, we see that 1 is in the set, meaning it's already part of a sequence, so we skip it. The same logic applies to the numbers 3 and 4, so we move on. Now, when we encounter the number 100, we check if 99 is in the set. Since it's not, 100 starts a new sequence. We initialize current_number to 100 and current_street to 1. Checking for 101, it's not in the set, so the sequence ends, and we update longest_streak to the maximum of its current value in current_streak, which remains 4. Similarly, for the number 200, we see that 199 is not in the set, so 200 starts a new sequence. We set current_number to 200 and current_street to 1. Since 201 is not in the set, the sequence ends, and again, longest_streak stays at 4. With no more numbers left to process, we return longest_streak, which is 4. In this second example, the input array is 1, 9, 3, 10, 4, 20, 2. We again start by converting it to a set, resulting in number_set equals 1, 2, 3, 4, 9, 10, 20. We initialize longest_streak to 0. The first number we process is 1. Since 0 is not in the set, 1 begins a new sequence. We set current_number to 1 and current_street to 1. Checking sequentially, we find 2, 3, and 4 in the set, incrementing current_number and current_streak each time. However, 5 is not in the set, so we end the sequence and update longest_street to 4. For the numbers 2, 3, and 4, we find they're already part of an existing sequence, so we skip processing them further. Next, we encounter the number 9. Since 8 is not in the set, 9 starts a new sequence. We initialize current_number to 9 and current_street to 1. We then find that 10 is in the set, so we increment both variables. However, 11 is not in the set, so the sequence ends, and we update longest_streak to the maximum of 4 and 2, which is still 4. After that, we process 20. Since 19 is not in the set, 20 starts a new sequence. We set current_number to 20 and current_streak to 1. Since 21 is not in the set, the sequence ends, and longest_streak remains 4. With no more numbers to process, we return longest_streak, which is 4. For the third example, the input array is empty, so when we convert it to a set, we get an empty set number_set equals. We initialize longest_streak to 0. Since there are no numbers in number_set, the loop does not execute. Without any sequences to process, we directly return longest_streak, which is 0. The time complexity of the algorithm is O(n), where n is the size of the input array. To understand this, let's break it down into the main steps. First, converting the input list nums into a set takes O(n) time, since each insertion into the set is an O(1) operation on average, and this is repeated for all n elements. Next, the algorithm iterates through the set using a for loop. Since the size of the set is at most n, the loop runs O(n) times in the worst case. Finally, for each element in the set, the condition if number 1 not in number_set is checked. This lookup operation is O(1) for each check, so across all elements, the total contribution to the time complexity is also O(n). These steps together give us a time complexity of O(n). Now let's analyze the inner while loop, which is responsible for expanding the consecutive sequence. This loop iterates through numbers in a sequence only once because the algorithm ensures each number is processed as the start of a sequence only if number 1 is not in the set. This design means that even when expanding sequences, each number in the input is handled just once, contributing another O(n) to the time complexity. Adding up all these steps, set construction, iteration through the set, and sequence expansion, the total time complexity remains O(n) overall. For space complexity, the algorithm primarily uses the set number_set, which stores up to n elements in the worst case, requiring O(n) space. The additional integer variables used, like longest_streak and current_number, require only constant O(1) space, which is negligible compared to the set. Therefore, the overall space complexity is O(n). Since the set is the dominant factor in space usage, our overall space complexity is O(n). Now let's examine the algorithm's performance across different cases. In the best case, when the input array nums is empty, the algorithm immediately returns 0. This results in a time and space complexity of O(1). In the average case, for a typical random input, the algorithm processes the elements of the set linearly, efficiently grouping elements into sequences. The time complexity remains O(n) due to the linear processing of elements. In the worst case, where the input array contains n unique numbers that form a single consecutive sequence, the algorithm iterates through all elements and expands the sequence fully, still resulting in an O(n) time complexity. Across all cases, the algorithm demonstrates consistent linear performance. When comparing this algorithm to a brute force approach, the differences become clear. A naive solution might involve sorting the array first, which has a time complexity of O(n) log n. After sorting, you would then iterate through the array to identify consecutive sequences. This approach not only takes more time but also requires additional space to store the sorted array. In contrast, the optimal algorithm presented here completely avoids sorting by leveraging a set for O(1) lookups and ensures that each number is processed only once. This allows us to achieve a time complexity of O(n), making this approach significantly more efficient and well-suited for handling large input sizes. To mathematically prove the algorithm's big O complexity, consider the key operations. First, the set operations, both insertions and lookups, are O(1) on average due to the hash-based storage. This ensures that the creation and use of the set remain efficient. Next, the total number of iterations is linear. Each number in the input is processed exactly once, either in the outer loop or during the sequence expansion in the inner while loop. Importantly, no number is revisited because sequences are expanded linearly from their starting points. Combining these factors, the total number of operations scales directly with the size of the input, confirming the overall time complexity is O(n). Similarly, the use of the set requires O(n) space, leading to a space complexity of O(n). This rigorous breakdown validates the algorithm's efficiency. When solving the longest consecutive sequence problem, there are several common mistakes to watch out for. First, using sorting might seem like a valid approach since it organizes the array, but it adds unnecessary overhead with a time complexity of O(n) log n. Sorting also struggles with duplicates and negative numbers, potentially leading to errors. Another frequent oversight is neglecting to handle negative numbers. Many assume inputs are strictly positive integers, but failing to account for negatives can disrupt sequence calculations. Inefficient brute force methods, such as checking every possible sequence starting at every element, can result in a prohibitive O(n) superscript 2 complexity, which is far too slow for large inputs. Additionally, ignoring edge cases like empty arrays, single-element arrays, or arrays filled with duplicates can lead to runtime errors or incorrect results. Lastly, overcomplicating the solution by using unnecessarily complex data structures can make the code harder to debug and maintain without offering performance benefits. Avoiding these pitfalls is key to crafting a robust and efficient solution. To approach consecutive sequence problems effectively, there are a few key insights to keep in mind. A critical pattern is leveraging a hash set for O(1) lookups, which allows you to efficiently determine if a sequence starts by checking whether x1 is absent from the set. This avoids redundant processing of intermediate elements. The optimal complexity for problems of this type is often O(n), achievable through hash sets or sliding windows, and reducing redundant computations is essential to reaching this efficiency. When discussing your approach in interviews, it's important to communicate the trade-offs of alternative methods like sorting or brute force, explaining why the linear approach is preferable. Always clarify input constraints such as whether duplicates, negative numbers, or the maximum array size are permitted, since misunderstanding these can lead to incorrect assumptions. Finally, manually testing your solution with small cases like single-element arrays, arrays with duplicates, or disjoint sequences can help validate your logic and catch potential edge cases early. There are also alternative approaches to solving this problem, each with its own trade-offs. The hash set approach is particularly effective. By storing all elements in a hash set, you can efficiently identify the start of a sequence by checking if x1 is not in the set, then expand the sequence to calculate its length. This method runs in O(n) time and space, making it optimal for large inputs, though it does require additional memory for the hash set. Another option is the sorting approach, where you sort the array and iterate through it to find consecutive sequences. While this method is simpler to implement and works in some cases, its O(n) log n complexity makes it less efficient, especially for larger inputs. Lastly, the sliding window approach can be useful in variations that require contiguous subarray properties. While it runs in O(n) time, it's better suited for ordered or contiguous problems and may not directly apply to unordered sequences like this one. Each approach has its strengths and weaknesses, so understanding when to use them is key to solving related problems effectively. Great job! To recap, we discussed the optimal solution to the longest consecutive sequence problem, leveraging hash sets for efficiency. Remember to practice similar problems to strengthen your skills further. Thanks for watching, and don't forget to like, share, and subscribe to stay updated with more coding tutorials. Happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!